Good afternoon. Today we're going to talk through lab number 2, traveling longitudinal waves and sound. My name is Ellie Rose.
I'm Katie Jane.
I'm Lisa.
I'm Abby.
The theory behind this week's lab was to measure the speed of sound using wavelength and frequency. Sound is a longitudinal wave that travels through a fluid medium such as air, propagating in all directions. The speed of sound depends on how far the wave travels during one full oscillation, which is described by the wavelength and the frequency. And these variables are related through the equation velocity equals wavelength times the frequency. Further, it can also be theorized that the expected speed of sound can be found by using the room temperature using the equation 331 meters per second plus the multiple of 0.6 times the temperature in Celsius in the room.
So for the purpose of the activities, on activity 1, we measured the wavelength using a specific frequency. In activity 2, we were trying to find the speed of sound based off of the wavelength and the frequency. And for activity 3, we used an equation given in the theory on how to calculate the speed of sound using the temperature that we took throughout the experiment at several times.
As you can see on the screen, we used lots of different types of equipment, but pay attention as I walk through the methods, as I will be mentioning each of those pieces. First of all, we set up our handy dandy Pasco here and Capstone software on a laboratory laptop. Now, in activity 1, we used a cute little miniature speaker and a sound sensor on a meter stick. We played a frequency of 2500 hertz and began to drag the sound sensor back across the meter stick, watching the screen as the sinusoidal waves come into phase. One of the waves represents sound intensity and the other represents voltage. As the waves come into phase, we marked the distance here and plotted each distance versus the trial, and the slope of that line gave us the wavelength. Now for activity 2, we did the exact same thing again, where we used 5 different frequencies played from our miniature speaker. For each of those frequencies, we repeated this motion, finding the distance, graphing the distance in the trial, which gave us the wavelength. Then we took all 5 wavelengths and plotted them against the inverse of the frequencies that we played, and the slope of that line gave us the speed of sound. Now in activity 3, we compared the speed of sound that we found with the speed of sound we found using the room temperature. We will not be using earplugs today. However, in our experiment, we used them, although the FDA says that the frequencies we played are harmless. Now, we're going to do a demonstration using the 2500 hertz from activity 1. Pay attention to the screen as the waves come into phase. The distances from the activities from beforehand can be seen on the screen at these specific distances, but for the purpose of this demo, we will do just a few of the distances.
Here in Pasco, you can see that I have the frequency set to 2500 as stated previously, and the amplitude is 5 volts, which just affects how loud the sound would be. So as you can see, these are very much in phase, and as Ellie Rose is moving it back, now they have become out of phase. And they're almost in phase again, and now they're in phase, and now they're getting out of phase again. Now they're in phase,
And now they're out.
Now we'll talk about our results and conclusions.
For activity 1, as we said before, we did it for 2500 hertz, and we were trying to find the wavelength as we were measuring when the sinusoidal waves were in phase. And as you can see on this graph, the x-axis is trial numbers, which just means the number of times on the meter stick that we measured they were in phase, and then the y-axis is in centimeters, the exact measurement that they were in phase. Our expected value of wavelength is based off of the expected velocity of sound, which is 343 meters per second, and then our slope from this graph was 13.73 centimeters compared to the known of 13.72 centimeters, and our percent error was 0.07%, which shows very high accuracy.
In activity 2, in our 5 trials, we used 5 frequencies to find the corresponding wavelengths of each, as shown on the screen. And you can see the different frequencies that we used and their wavelengths. The 5 trials were very precise, as seen by the high R-squared values. Then we graphed the previously 5 found wavelengths from the slopes of the previous graphs and plotted them versus 5 inverse frequencies. As seen on this graph, the slope was around 334 meters per second. When compared to the known value of 343 meters per second, we found a percent error of about 2.67, and this showed high accuracy. Furthermore, it can be seen that the R-squared value from this graph showed high precision.
So for activity 3, we measured the speed of sound, which for us was 345 meters per second. And the room temperature that we used to get that value was 22.7 degrees Celsius from our average. And our percent error was 3.13%, which shows high accuracy. However, some sources of random, systematic, and human errors within this lab can include extra noise that was in the room, estimating when waves are in phase as looking, and then estimating the distances on the meter stick, and error also from the least count scale when reading the meter stick or the thermometer. Both could have been in play.
Our above and beyond discusses different parts of sound that we did not talk about. One of those is as far as volume goes. I mentioned earlier that we used a constant amplitude of 5 volts, but you can change that. Smaller amplitudes create quieter volumes, and larger amplitudes create louder volumes. As for pitch, we observed this during activity 2 when we were changing frequency. The shorter frequencies, or longer wavelength, results in deeper pitches, and then higher frequencies or shorter wavelengths results in higher pitches. What we did not talk about at all was harmonics and how this relates to frequency. You have a fundamental frequency, and this can create harmonics that are multiples of the fundamental frequency. So you have the first harmonic is twice the fundamental frequency, and the second one is 3 times the fundamental frequency, and then it keeps going from there. This plays into different instruments and how they make different notes sound different, and sometimes different instruments make the same note, but it sounds slightly different, and that is because of the different harmonics. Different instruments make different combinations of harmonics, and so then we get the glorious music that we enjoy.
We would like to thank you for listening to our presentation, and we concluded that frequency, wavelength, and room temperature all have an impact on the speed of sound.